Design and analysis of shell and tube type heat exchanger. Abstract shell and tube heat exchangers are having special importance in boilers, oil coolers, condensers, preheaters. They are also widely used in process applications as well as the refrigeration and air conditioning industry. The robustness and medium-weighted shape of shell and tube heat exchangers make them well suited for high-pressure operations. The basic configuration of shell and tube heat exchangers, the thermal analysis and design of such exchangers form an included part of the mechanical, thermal, chemical engineering scholars for their curriculum and research activity. This report presents the application of differential evolution, DE, for the optimal design of shell and tube heat exchangers. The main objective in any heat exchanger design is the estimation of the minimum heat transfer area required for a given heat duty, as it governs the overall cost of the heat exchanger. Many configurations are possible with various design variables such as outer diameter, pitch, and length of the tubes, tube passes, baffle spacing, baffle cut, etc. Hence the design engineer needs an efficient strategy in searching for the global minimum. 1. Introduction. Heat exchangers are used to transfer thermal energy between two or more media and widely applicable to chemical industries, food industries, power engineering, and so on. The shell. Process fluid assignments to shell side or tube side. Selection of stream temperature specifications. Setting shell side and tube side pressure drop design limits. Setting shell side and tube side velocity limits. Selection of heat transfer models and fouling coefficients for shell side and tube side. Selection of heat exchanger TEMA layout and number of passes. Specification of shell side parameters, materials, baffle cut, baffle spacing. And tube heat exchanger is the most common heat exchanger type, therefore the study of its design and analysis is of great importance for conserving energy in heat exchange process. Shell and tube heat exchangers are having special importance in boilers, oil coolers, condensers, preheaters. They are also widely used in process applications as well as the refrigeration and air conditioning industry. The robustness and medium-weighted shape of shell and tube heat exchangers make them well suited for high-pressure operations. The basic configuration of shell and tube heat exchangers, the thermal analysis and design of such exchangers form an included part of the mechanical, thermal chemical engineering scholars for their curriculum and research activity. Shell and tube heat exchangers are used extensively throughout the process industry and such a basic understanding of their design, construction, and performance is important to the practicing engineer. The optimum thermal design of a shell and tube heat exchanger involves the consideration of many interacting design parameters which can be summarized as follows. 1.1 Process. Specification of tube parameters, size, layout, pitch, and material. Setting upper and lower design limits on tube length. One of the important processes in engineering is the heat exchange between flowing fluids, and many types of heat exchangers are employed in various types of installations, as petrochemical plants, process industries, pressurized water reactor power plants, nuclear power stations, building heating, ventilating, and air conditioning and refrigeration systems. As far as construction design is concerned, the tubular or shell and tube type heat exchangers are widely in use. The shell and tube heat exchangers are still the most common type in use. They have larger heat transfer surface area to volume ratios than the most of common types of heat exchangers, and they are manufactured easily for a large variety of sizes and flow configurations. They can operate at high pressures, and their construction facilitates disassembly for periodic maintenance and cleaning. The shell and tube heat exchangers consist of a bundle of tubes enclosed within a cylindrical shell. One fluid flows through the tubes and a second fluid flows within the space between the tubes and the shell. Typical shell and tube heat exchanger is shown in Figure 1.1. Heat exchangers in general and tubular heat exchangers in particular undergo deterioration in performance due to flow maldistribution. The common idealization in the basic tubular heat exchanger design theory is that the fluid is distributed uniformly at the inlet of the exchanger on each fluid side throughout the core. However, In practice, flow maldistribution is more common and significantly reduces the idealized heat exchanger performance. 1 shell pass and 1 tube pass. Fig.1-1 shell and 1 tube pass heat exchanger. Fig.2 shell and tube heat exchanger. 2 Problem summary. Inlet raw water temperature equals 20 degrees Celsius. Inlet raw water pressure equals 7.01 bar. Mass flow rate of raw water equals 150 kg/sec. Inlet city water temperature from supply equals 32 degrees Celsius. Inlet city water pressure equals 5.75 bar. Mass flow rate of city water equals 50 kg/sec. Thermal conductivity of 0.5 cr alloy tube equals 42.3 W/mk. Outlet city water temperature equals 25 degrees Celsius. The maximum flow velocity through the tube is also suggested to be 2 m/sec to prevent erosion. 3 Literature review. Wilfried Rochel, Chukrat N. A. Ranang, 1 calculated the axial temperature profiles in a shell and tube heat exchanger binumerically for given maldistributions on the tube side. For comparison, the same maldistributions are handled with the parabolic and hyperbolic dispersion model with fitted values for the axial dispersion coefficient and third sound wave velocity. The analytical results clearly demonstrate that the hyperbolic model is better suited to describe the steady-state axial temperature profiles. Sahu, R.K., and Wilfried Rochel, 2 derived the fundamental equations of hyperbolic model and its boundary conditions in terms of cross-sectional mean temperature from the basic equations of heat exchanger, the traditional parabolic model and the proposed hyperbolic model, which includes the parabolic model as a special case, can be used for dispersive flux formulation. Instead of using the heuristic approach of parabolic or hyperbolic formulation, these models can be quantitatively derived from the axial temperature profiles of heat exchangers. In that paper, both the models are derived for a shell and tube heat exchanger with pure maldistribution, without backmixing, in tube side flow and the plug flow on the shell side. The Mach number and the boundary condition, which plays a key role in the hyperbolic dispersion, have been derived and compared with previous investigation. It is observed that the hyperbolic model is the best suited one as it compares well with the actual calculations. This establishes the hyperbolic model and its boundary conditions. Wilfried Rochel, and Chukrat N. A. Ranang, 3 tested and compared the newer hyperbolic dispersion model and parabolic model, considering the processes with pure maldistribution, without backmixing, on the tube side of a shell and tube heat exchanger and plug flow on shell side. The boundary conditions of the model equations are discussed in detail for the steady state, and equations of the axial temperature profiles are provided in the programmable form. For the hyperbolic model, simple relationships between the model parameters are derived. Considering the transient adiabatic processes in the tube bundle, a concept for the experimental determination of the model parameter m, the third sound Mach number, is developed. Authors concluded that for an overall consideration of a heat exchanger with maldistribution, the parabolic model is satisfactory. The parameter p-par depends on both NTUs of the heat exchanger, which makes the model difficult to handle. The advantage of the parabolic model is that only one parameter is needed. The hyperbolic model is superior to the parabolic model because it predicts the axial temperature profiles correctly, especially temperature jumps and positive slopes. Umingsuan, Wilfried Rochel, 4 applied the dispersion model is to the description of the effects of shell and tube side flow maldistribution. By means of this model, an efficient and versatile method of predicting transient response of multi-pass shell and tube heat exchangers is developed. The method allows for effect of maldistribution on transient process, influence of heat capacities of fluids and solid components, arbitrary inlet temperature variations and step disturbances of flow rates. General forms of initial conditions and 2 different flow arrangements are considered. A general form of the solution for steady state and dynamic simulation is derived. Temperature profiles are determined with numerical inversion of the Laplace transform. Some examples are calculated and the effect of maldistribution is discussed. Flow maldistribution hinders transient responses to any inlet changes and Decreases thermal effectiveness of heat exchangers. Its effect becomes more remarkable with increasing NTC. The Peclet number has been used to quantitatively describe this kind of effect. The calculation has shown that the dispersion model should be applied instead of the plug flow model if PE55. 4 basic principles of design. First, of course, the heat exchanger must meet the process requirements. That is, it must affect the desired change in thermal condition of the process stream within the allowable pressure drops, and it must continue to do this until the next scheduled shutdown of the plant for maintenance. Second, the exchanger must withstand the service condition of the plant environment. This includes the mechanical stresses of installation, startup, shutdown, normal operation, emergencies, and maintenance, and the thermal stresses induced by the temperature differences. It must also resist corrosion by the process and service streams, as well as by the environment. This is usually mainly a matter of choice of materials of construction, but mechanical design does have some effect. Desirably, the exchanger should also resist fouling, but there is not much the designer may do with confidence in this regard except keep the velocities as high as pressure. Third, the exchanger must be maintainable, which usually implies choosing a configuration that permits cleaning tube side, as may be indicated, and replacement of tubes and any other components that may be especially vulnerable to corrosion, erosion, or vibration. This requirement may also place limitations on positioning the exchanger and in providing clear space around it. Fourth, the exchanger should cost as little as is consistent with the above requirement. In the present context, this refers to first cost or installed cost, since operating cost or cost of lost production due to exchanger unavailability have already been considered by implication in the earlier and more important criteria. Finally, there may be limitations on exchanger diameter, length, weight, and or tube specification due to site requirements, lifting and servicing capabilities, or inventory consideration. 5. Generalized design procedure of heat exchanger. Process conditions, stream compositions, flow rates, temperatures, pressures, must be specified. Required physical properties over the temperature and pressure ranges of interest must be obtained. The type of heat exchanger to be employed is chosen. A preliminary estimate of the size of the exchanger is made, using a heat transfer coefficient appropriate to the fluids, the process, and the equipment. A first design is chosen, complete in all details necessary to carry out the design calculations. The design chosen is now evaluated or rated, as to its ability to meet the process specifications with respect to both heat duty and pressure drop. Based on this result, a new configuration is chosen if necessary, and the above step is repeated. If the first design was inadequate to meet the required heat load, it is usually necessary to increase the size of the exchanger, while still remaining within specified or feasible limits of pressure drop, tube length, shell diameter, etc. This will sometimes mean going to multiple exchanger configurations. If the first design more than meets heat load requirements or does not use all the allowable pressure drop, a less expensive exchanger can usually be designed to fulfill process requirements. The final design should meet process requirements, within the allowable error limits, at lowest cost. The lowest cost should include operation and maintenance costs and credit for ability to meet long-term process changes as well as installed, capital, cost. Exchangers should not be selected entirely on a lowest first cost basis, which frequently results in future penalties. 6. Basic design procedure of heat exchanger. Fig.3 Basic design procedure of heat exchanger. 7. Component of shell and tube heat exchanger. 7.1 Why a shell and tube heat exchanger? Shell and tube heat exchangers in their various construction modifications are probably the most widespread and commonly used basic heat exchanger configuration in the process industries. The reasons for this general acceptance are several. The shell and tube heat exchanger provides a comparatively large ratio of heat transfer area to volume and weight. It provides this surface in a form which is relatively easy to construct in a wide range of sizes and which is mechanically rugged enough to withstand normal shop fabrication stresses, shipping and field erection stresses, and normal operating conditions. There are many modifications of the basic configuration, which can be used to solve special problems. The shell and tube exchanger can be reasonably easily cleaned, and those components most subject to failure, gaskets and tubes, can be easily replaced. Finally, good design methods exist, and the expertise and shop facilities for the successful design and construction of shell and tube exchangers are available throughout TTHE world. 7.2 Basic components of shell and tube heat exchangers. 7.2.1 Tubes. The tubes are the basic component of the shell and tube exchanger, providing the heat transfer surface between one fluid flowing inside the tube and the other fluid flowing across the outside of the tubes. The tubes may be seamless or welded and most commonly made of copper or steel alloys. Other alloys of nickel, titanium, or aluminum may also be required for specific applications. 7.2.2 Tube sheets. The tubes are held in place by being inserted into holes in the tube sheet, and they're either expanded into grooves cut into the holes or welded to the tube sheet where the tube protrudes from the surface. The tube sheet is usually a single round plate of metal that has been suitably drilled and grooved to take the tubes, in the desired pattern, the gaskets, the spacer rods, and the bolt circle where it is fastened to the shell. However, where mixing between the two fluids, in the event of leaks where the tube is sealed into the tube sheet, must be avoided. 7.2.3 Shell and shell side nozzles. The shell is simply the container for the shell side fluid, and the nozzles are the inlet and exit ports. The shell normally has a circular cross-section and is commonly made by rolling a metal plate of the appropriate dimensions into a cylinder and welding the longitudinal joint, rolled shells. Small diameter shells, up to around 24 inches in diameter, can be made by cutting pipe of the desired diameter to the correct length, pipe shells. The roundness of the shell is important in fixing the maximum diameter of the baffles that can be inserted and therefore the effect of shell to baffle leakage. Pipe shells are more nearly round than rolled shells unless particular care is taken in rolling. In order to minimize out of roundness, small shells are occasionally expanded over a mandrel. In extreme cases, the shell is cast and then bored out on a boring mill. 7.2.4 Tube side channels and nozzles. Tube side channels and nozzles simply control the flow of the tube side fluid into and out of the tubes of the exchanger. Since the tube side fluid is generally the more corrosive, these channels and nozzles will often be made out of alloy materials, compatible with the tubes and tube sheets, of course. They may be clad instead of solid alloy. 7.2.5 Channel covers. The channel covers are round plates that bolt to the channel flanges and can be removed for tube inspection without disturbing the tube side piping. In smaller heat exchangers, bonnets with flanged nozzles or threaded connections for the tube side piping are often used instead of channels and channel covers. 7.2.6 Pass divider. A pass divider is needed in one channel or bonnet for an exchanger having two tube side passes, and they are needed in both channels or bonnets for an exchanger having more than two passes. If the channels or bonnets are cast, the dividers are integrally cast and then faced to give a smooth bearing surface on the gasket between the divider and the tube sheet. If the channels are rolled from plate or built up from pipe, the dividers are welded in place. The arrangement of the dividers in multiple pass exchangers is somewhat arbitrary, the usual intent being to provide nearly the same number of tubes in each pass, to minimize the number of tubes lost from the tube count, to minimize the pressure difference across any one pass divider, to minimize leakage and therefore the violation of the MTD derivation, to provide adequate bearing surface for the gasket and to minimize fabrication complexity and cost. 7.2.7 Baffles. Baffles serve two functions. Most importantly, they support the tubes in the proper position during assembly and operation and prevent vibration of the tubes caused by flow-induced eddies, and secondly, they guide the shell side flow back and forth across the tube field, increasing the velocity and the heat transfer coefficient. Fig.4 Shell and Tube Heat Exchanger. 8 Design and Analysis. The properties of the tube side fluid at 20 C from Appendix B, R, equals 4182. K equals 0.598 W slash equals 7.01 equals 998.2 kg slash equals 10.02 times. The properties of the shell side fluid at average temperature from the appendix are: Cp equals 4179 J slash kg. K equals 0.612 W slash M2. PR equals 5.75 equals 995.9 kg slash M3 equals 8.15 times 10-4 N.S slash M2. To solve the problem, first estimate the number of tube. MT equals .MACNT. NT equals M slash .MAC. Equals 4 MT slash .PM. Equals 4 times 150 slash 998.2 times P times 0.016, 2 times 2. Equals 373.88. NT equals 374. The flow area through the tube is at equals P slash 4 times NT equals P, 0.016, 2 slash 4 times 374. Equals 0.075 M2. Now estimate the shell diameter from EQ. Equals NT, CL, PR, 2, slash 0.785, CTP. CTP equals 0.93. CL equals 1.0. DS equals 374 times 1 times, 2.54 times 10-2 slash 1.9 times 10-2, 2, 0.019, 2 slash 0.785 times 0.931 slash 2. Equals 575 mm. Which is rounded off as 580 millimeters. The selected and estimated constructional parameter can be summarized as shell inside diameter. ds equals 0.58 m. Number of tubes. NT equals 1. Tube outside diameter do equals 19 mm. Tube inside diameter. D1 equals 16 mm. Square the pitch. PT equals 0.0254 m. Baffle spacing. B equals 0.5 m. Kern method estimate the cross-flow area at the shell diameter. As equals ds ntcd0, b. Where, ntc equals ds slash pt. Equals 580 slash 25.4. Equals 22.83. As equals 0.58-22.83 times 0.019, times 0.5 equals 0.073 m2. The equivalent diameter can be calculated from x. D equals 4, p slash 4, slash pd0. Equals 4. Equals 0.024 m. Calculate the Reynolds number. Re equals. Equals times equals 20,169.76. Assuming constant properties, the heat transfer coefficient can be estimated from EQ. Ho equals Re 0.55 PR1 slash 3 equals 20,169.76, 0.55, 5.57, 1 slash 3 equals 3793.6 W slash M2.K. Tabarek method. Consider the following. Tabarek gives the following correlation for the shell side heat transfer coefficient for turbulent flow. Nu equals 0.2 Re 0.6 PR 0.4. Where the Reynolds number is based on the tube outside diameter and the velocity on the cross-flow area at the diameter of the shell. Res equals 15967.8. Nu equals 0.2, 15,967.8, 0.6, 5.57, 0.4 equals 132.2. HS equals 4259.09 with M2.K. Bell-Delaware method. The shell side heat transfer coefficient is given by EQ. HTD equals JIPS 2/3. 0.14. Where G equals 0.37 res 0.395. Where res equals 15967.8. G equals 0.37 res 0.395 equals 0.0081. Who equals 0.00814179, 2/3. Who equals 7382.8 W/M2.K. It is assumed that the properties are constant. In the Bell-Delaware method, the correction factors due to bypass and leakage stream are provided in graphical forms depending on the constructional features of the heat exchanger. Let us assume that combined effect of all these correction factory is 60%. Ho equals 0.60 W/M2.K. Therefore, the three above method have demonstrated comparable results to estimate the shell side heat transfer coefficient. Tube side heat transfer coefficient. REI equals 31878.6. The tube side heat transfer coefficient can be calculated from the Patukhov-Kirillov correlation. The overall heat transfer coefficient for the clean surfaces